Hello, welcome back to Organic Chemistry. My name is Todd Rothman, and in this video, we're going to learn about potential energy. Now, this is the first of 3 sections for the cycloalkane conformations. And one of the first things I want to mention is that I assume that you watched the alkane conformations first, because this video carries a lot of information, a lot of the building blocks that we did then. We're going to bring it into this video set, and it's going to be assumed that you've watched the alkane conformations first, and then you went in and you're watching this one, which is the cycloalkane conformations. Now, in that video series with the alkane conformations, I introduced the idea of potential energy. This video, we're going to go further into potential energy. We're going to learn more about it, and we're going to also learn how we measure potential energy. And that's the goal for this first of 3 sections. So let's get started. Now, the first thing I want to mention is, of course, we're referring to potential energy with a focus of inside rings. But the idea of potential energy applies to any molecule, and it doesn't have to be a ring system, right? So whatever information I show you at this particular video set applies to all different type of molecules, but we're going to focus in on rings and see what unique characteristics they have. And it turns out that, remember, potential energy is the energy stored in a system. Now, in molecules, it's stored within the bonds. And what happens is there's this energy stored that's trying to be released. And when you break a bond or you do something to alter the atomic configuration, it can release that potential energy. Now remember, I gave you an analogy of a rubber band. If a rubber band is at rest, it's no potential energy. But when you pull it and you hold, now the rubber band has potential energy in the system. It wants to go back to its resting state. So if you let go of the rubber band, it pushes back to its resting state. And that releases potential energy and converts it into heat, actually. So potential energy is the energy stored in the system, in our case molecules, and we're going to figure out how we can release that potential energy. But first we got to figure out what makes potential energy, and that's what this is here. So these are the ring strains. These are the strains that contribute to the potential energy of a system. And the first one is called the angle strain. And actually, this is the one unique strain that ring systems have, and that alkanes, what we referred to before, they don't have. But the other two, everybody has. So angle strain, think of it this way. If you have a carbon and it's sp3, it wants to be 109.5 degrees, right? So if you take those 2 atoms, or let's say the carbon that's got its 109 for its bond angles, and you either change it, you reduce it, make it less than 109, or you increase it, you expand it, you make it more than 109, then that's changing the configuration of the orbitals, and it's not ideal. It winds up, remember, because when we figure out 109.5 for sp3 carbon, we did that by thinking about the valence shell electron pair repulsion theory. What is the best place for electrons when you have 4 pairs to deal with, right? In the case of carbon, so with 4 single bonds. And so we came up with these numbers, and that is the best for the separation of these electrons. If you expand or reduce that angle, then you're bringing the electrons closer than they want to be. Now, from an orbital point of view, when you change the angle, the orbitals of the 2 atoms that are connected together, they start to they're not overlapping anymore. So there's not such a strong overlap. They start to go off alignment, and that in turn increases the energy because there's not a good overlap between the 2 atoms. So this is the idea. This is the angle strain that we deal with in ring systems, and we'll see examples soon. Now, the next one is torsional strain. And remember, we went through a whole detail. And at the very end, the last section of the alkane conformations, we went over the idea of the orbital description. And what we found was that in a staggered configuration, that the neighbor electrons of one neighbor atom and its neighbor that does not have electrons in it, the anti-bonding MO. So the bonding MO electrons and the anti-bonding MO electrons, they can interact together so that the electrons from the BMO can go into the ABMO, the anti-bonding MO. And that can only happen if it's staggered. We found out if none of this makes sense, go to section 3 of alkane conformations and you'll see all the details. Okay, so we found that in staggered, you have this stability characteristic, this ability to transfer electrons over into the anti-bonding molecular orbital. Now, when it's eclipsed, you don't have that ability. The orbitals are not lined up properly. They're not matching. So when you go from a staggered, where you have electrons jumping back into the ABO and back and forth, and then you turn it to eclipse, and now the electrons are restricted, you've made more potential energy. Because remember, the more electrons can travel, the lower the potential energy will be, because they have more freedom, less repulsion. Okay? So that's the idea. That's one part of torsional. So when you're taking a system, I don't have the molecule with me, but when you're taking a system and you go from eclipse, staggered, where they're up and down, let's say, and you rotate it to become eclipse, as it goes into that eclipse, it loses the ability to travel its electrons to its neighbor. So as it rotates, now the electrons are restricted. And that energy change from going from freedom to restriction of freedom is called the torsional barrier. And that's torsional strain. Now, another part of torsional strain is the sterics. So when you're going up and you're making the two atoms come close together, we learned that there's a steric issue there as well. There's a repulsion of electron clouds. So the combination of this hyperconjugation reduction, remember that's called hyperconjugation when you take electrons and move them into an antibonding orbital neighbor. So hyperconjugation reduction and increase of steric issues is what creates torsional strain. Okay, so that's a long-winded description, but the idea here, like I mentioned, is that I went through every detail very carefully in section 3 of the alkane conformation. So the last one is steric, which is also known as a gauche interaction. Now remember, that's when you have orbitals that are coming close together. So this is part of that van der Waals repulsion concept. So as electron clouds come together, they're going to start to repel each other because the electrons are starting to sense each other. Okay, so there's a nice distance that makes it perfect, and that's called van der Waals attraction. And that's what actually creates these intermolecular forces that we learn about. But if it gets too close together, they start to repel. Van der Waals repulsion. All right, so these are the three important characteristics that make up the potential energy within a system. Okay, there are other things to consider, but these are the three that we need to know right now. And so now let's take this, and by the way, recognize that the only unique strain for a cycloalkane compared to an alkane is this angle strain. So in a ring, they have they're forcing themselves into a certain angle. Alkanes have rotation. They could change their angle, no problem, to kind of give itself freedom, but rings don't. They're restricted. So once you lock into a ring, the carbons that make up that ring and all of its bonds are locked in within, you know, a certain amount of margin in those angles that we see. Okay, so the next thing is, how do you measure potential energy? This is really important because we're going to use this concept throughout the whole year. Okay, now measuring potential energy is important because it tells us something about our reactants. Now, if a reactant has a lot of potential energy, then number one, it's unstable. But number two, it's very reactive, because things that have energy built up within it, it wants to release that energy. And the way it does that is by reacting or doing something, okay, to change that state that it's in. So they're very reactive. And that's what I wrote here. The greater the potential energy, the less stable and the more reactive. So it is important that we can calculate the potential energy of systems. Now, just getting a rough generalization of, you know, is this more reactive than that one? Or which one's more likely to have higher energy state as is? And so we'll have to use tools to figure that out. Now, here's the problem. Potential energy is not something that we can directly measure. We can't see it, and we can't run experiments on it. You can't kind of go in there and ask the bonds, how much energy do you have right now stored inside of you? So what we do is we do indirect analysis. Now, we know that when a system releases its potential energy, it's going to do that by way of heat. So when a system releases its potential